Welcome to this explainer. Today, we're diving straight into the invisible engines driving our entire universe, the kinetic particle theory. I know, we all know the basics, but we're going to break down exactly how these microscopic mechanics literally dictate the macro reality we experience every single day. Here's our roadmap for today. We'll cover the invisible building blocks, the rules of kinetic theory, solids, liquids, and gases, the great particle escape, and finally, squeezing and heating gases. Let's get to it. So we are going to start with this absolutely fascinating question drawn directly from our sources. How can an element exist in three completely different states simply through a change in temperature? Think about it. How does heat, just heat, transform something rock hard into something completely invisible? Section 1. The invisible building blocks. To answer that question, we need to zoom all the way in. Okay, we all know the absolute foundation here. Matter is divided into unbelievably small particles. The atom, defined as the smallest possible piece of an element capable of taking part in a chemical reaction, is exactly where our kinetic story begins. And when atoms from different elements link up and are held together by covalent bonds, boom, we get molecules. It is pretty wild to think that the highly structured sugar crystals in your morning coffee or the salt on your food get their massive variety from how these elements organize at this super fundamental level. So how do these tiny atoms and molecules actually scale up to create the solids, liquids, and gases we interact with? Well, that's exactly where kinetic particle theory comes in. It's a theory that accounts for the bulk properties of these states of matter entirely through the movement of particles. Section 2. Rules of kinetic theory. Let's lay down the ground rules for how these particles behave. The absolute golden rule here: particles are never, ever still. Looking at these main points, it literally all hinges on energy. Matter is made of small particles that are always moving. You ramp up the temperature, and you ramp up their average kinetic energy. That freedom of movement is what defines their state. And get this, even gas pressure is simply the result of these microscopic pinballs constantly slamming into the walls of their container. Section 3. Solids, liquids, and gases. Now that we know the rules, let's see how they translate to the visible world. This perfectly illustrates our theory in action. Just look at the basic differences in their physical properties. Solids are rigidly fixed in shape and simply cannot flow. Liquids, on the other hand, flow as fluids to take the shape of their container, even though they keep a definite volume. And then you have gases, fluids that spread boundlessly throughout their container, possessing no definite volume whatsoever. To use a crowd analogy to really help visualize this, think of a solid as a tightly packed seated stadium audience. Everyone is totally fixed in place, right? A gas, by contrast, is like a chaotic, incredibly energetic mosh pit filling every possible corner of the room. It has no definite volume, it's totally fluid, and it just spreads everywhere. Section 4. The Great Particle Escape. So what happens when we introduce a little conflict and change to these distinct states? Adding energy completely shakes things up. When you do that, the faster-moving particles can physically break free from the surface of a liquid and escape. That right there is evaporation in action. Kinetic energy is literally launching particles out of one state and directly into another. Section 5. Squeezing and heating gases. Gases are incredibly sensitive to outside forces. Let's look at why. Because gases have so much empty space between their energetic particles, we get this really direct cause and effect chain. If the temperature is raised, gas particles move much faster and a lot more freely. They have less interaction with each other. The result? Those gas particles expand to occupy a much greater volume. It's that simple. But hey, it's not just temperature. Pressure is a massive factor too. When you have high pressure, particles are pushed much closer together. They take up a smaller volume and they're way more likely to interact. Drop to low pressure, and the particles occupy greater space and are way less likely to interact. It's the exact same microscopic dance happening inside an aerosol can. We have seen today that the visible world is really just a macro expression of micro movements all fueled by heat, which leaves us with this final, kind of mind-bending thought. If higher temperature dictates faster movement, what happens to the very fabric of matter at the absolute coldest temperature possible? If we strip away all heat, does the movement of the universe simply stop? Keep that in mind next time you look at the world around you. Thanks for joining me for this explainer.